So we continue proving the theorems. Theorem 3, it says that every second countable regular space is normal. So recall the definition of second countability. A topological space that admits a countable basis is called a second countable, and regular means every point can be separated from closed sets by open sets. Okay, so that is more precisely, if X is a topological space and X is a point in the space X, and B is closed subset of X such that little x is not in B, okay, then there exist two disjoint open sets U and V such that X is in U and the closed set B is contained in the open set V. That is, for every pair of a point X and closed set B such that X is not in B, there are disjoint open neighborhoods of X and B respectively. Okay. So this is the definition of a regular space. So here our assumption is made. A topological space X is second countable and regular. Then what to prove? We have to prove that X is normal. Okay. So this is our assumption. X is regular space with a countable basis, that is regular and second countable. Second countable, that's why it has a countable basis. Okay, so our assumption is X is regular with a countable basis, script B. So what to prove? So we have to prove X is normal, that is for every. So suppose A and B, these are closed subsets of X and they are disjoint. They are disjoint closed subsets of X. So A, B, they are closed and they are disjoint with. This is the condition: A intersection with B equal to empty. That is, they are disjoint. So what to prove? So we have to prove X is normal. That is, we have to show that there exist open subsets. We denote them by U and V. So there exist U and V open subsets in X such that A contained in U and B contained in V, and they are disjoint. That is, so they are disjoint open neighborhoods of A and B respectively. So there exist disjoint. So to show there exist disjoint open neighborhoods of A and B respectively, where A and B, they are disjoint closed sets in the space X. Okay. So now let us consider an arbitrary point little x in the set A. So little x is in A means little x is not in B, okay, because they are disjoint. So little x, this point is in the complement of B. So x is in A and A subset of B complement. So x is in B complement. So B is closed, so B complement, that is open. Therefore, there exist some open subset U of X containing the point X such that U actually is subset of B complement, that is U intersection with B equal to empty set. Okay, so there exists, this is the definition of openness. So there exists some open subset of X containing the point X such that U contained in B complement, that is U intersection with B equal to empty set. Okay. Now we use the characterization theorem for regular spaces. So for this open set in X containing X little x, there exists some smaller open set V containing X such that closure of V is contained in U. So this is characterization. So here we apply a characterization theorem for regular spaces. So that is characterization theorem for regular spaces implies there exists some smaller open set V containing X such that V closure is contained in U. Now V is open. Okay, V is open and X belongs to V. So by definition there exists some basic open set, and this is script B. This is a basis, countable basis of the topological space X. So there exists some basic open set. We denote it by OX such that OX is subset of V. Okay, OX subset of V and OX is open neighborhood of X. So X belongs to OX. This is OX contained in V, and this part is characterization of so by characterization of regular spaces. So V is subset of V closure and V closure contained in U. So this is the last point. This is the characterization theorem. V closure contained in U. Okay, so we have this. So what is the summary? Summary is following. For every point X in the set A, there exists an open set OX, basic open set OX containing the point little x such that OX closure is disjoint from B. Okay, so here you see U is disjoint. So U has disjoint. So U has empty intersection with B. Okay, so U intersection U is disjoint from B, and so every subset of U disjoint from B. So in particular, this V is so V closure V and OX every subset of U disjoint from B. Okay, so OX closure intersection with B equal to empty set. Okay, so what we have. So this is the summary. For every X we have some basic open sets OX containing X such that closure of that basic open set OX has empty intersection with B. Okay, so we construct such a countable collection so of basic open sets. So here we have denoted this kind of sets OX by UN. Okay, so this is a subcollection of basic open sets of subcollection of this script B such that this is open cover. So open cover of A such that UN closure intersection with B equal to empty set. Okay. So we could denote. So we could denote this basic open set by ON also, but but here we have denoted by UN. So basically from this summary, so we have constructed. So what we do, construct such a countable open covering. So for every X we take one basic open set in B. Okay, so such that closure of that basic open set has disjoint, so has empty intersection with this closed set B, and the point is in that basic open set. Okay, so so such a sub collection is countable because this is countable set of all basic open sets. This is countable, so this is sub collection. So this is also countable. So we can represent this countable collection of uh, open sets, that is a covering of A by UN. Okay, so similarly we construct countable open covering Vn of Vn. This is set Vn. So n is in set of naturals. So this is countable collection. Okay, of open sets. So these are countable collection of basic open sets. That is the covering of B. And what properties? So what property of the elements in this covering has? That is V enclosure intersection with A equal to empty for all n. Okay, so for all n, so for every element, so has closure has empty intersection with A. Okay, now we define U1 prime equal to U1 set difference V1 closure. So U2 prime equal to U2 minus V1 closure union with V2 closure, and so on. In general, for Un prime equal to Un set difference, the finite union Vi closure I equal to 1 to n. So this is so every Un prime this is this open set because Un is open and this is finite. So finite in union of closed sets. So Vi closure I equal to 1 to n. This is finite union of closed sets. So this is closed. So open set minus closed set. This is open. Okay. So Un prime is open for every n equal to 1, 2, 3, and so on. And similarly, we define Vn prime equal to Vn set difference Ui closure I equal to union Ui closure I equal to 1 to n. This is also, so this is collection. So open sets Vi prime, Vn primes, these are open sets. Now we define U equal to union Un primes and V equal to Vn, union Vn prime over n. Okay. Now then one can see that these are so of course these are open sets U and V because union of open sets is open. So these are open sets and these are disjoint open sets such that A contained in U and B contained in V. So I would give an exercise. Please check that these are disjoint and open neighborhoods of A and B respectively. So these are disjoint open neighborhoods of A and B respectively. So checking their disjoint and so basically these are open. That is obvious because as union of open sets is open, and proving U and B are disjoint and they are open neighborhoods of A and B. So this is quite easy. So I give you an exercise. So please exercise. So that exercise will complete the proof. So this completes the proof. So now this is the last theorem in this set of slides. So this is the statement is every well ordered set X is normal in the ordered topology. Okay. So X is well ordered set. So what is well ordered set? So this is ordered set with well ordering property. That means every non-empty set of X has so every non-empty subset of X has least element. Okay, so equipped with ordered topology, X is normal if the order is well ordered. Okay, so let us prove it. So this is a fact we shall use in the proof. So open X, close Y. This is open subset of X in the order topology. So the argument proving this statement, this is open if X has X has largest element and Y is that largest element of X, then you know this is basic open set, because open X comma infinity, positive infinity, that is basically equal to open X comma close Y. Okay, so this is by definition. So by definition, so when X has largest element and Y is the largest element, then this is basic open set, okay, in the order topology. Now in the case when Y is not largest element, okay, Y is not largest element. So if Y is not largest element, then we have some Y prime that is the immediate successor of the element Y. So why such immediate successor exists, that is an exercise. So basically if Y has no immediate successor, then one can construct a non-empty subset of X that has no least element. So that would contradict that X is well ordered set. Okay, so this is an exercise, so that such an immediate successor of Y in X does exist. Okay, so here we apply X is well ordered. Okay, so anyway, this is the fact. Open X comma Y close Y, that is open set in the order topology on X. So now we prove that X is normal. So as earlier we considered two arbitrary disjoint closed subsets A and B of X, that is consider A comma B closed subsets of X with A intersection with B equal to empty set, that is their disjoint. So okay, so now suppose A naught denotes the smallest element of X, and so this is the case. So suppose this is smallest element of X, and the smallest element A naught is not in A or not in B. So enough to consider A naught is not in A. So then we can interchange the role of A and B. So A intersection B is empty set. Okay, so in this case we consider the smallest element is not a member of the closed sets A and B. Now for each point little a in closed set A, we have basic open set. So this is basic open set XA comma A. Okay, intersection with B equal to empty set. So why this is why such basic open set containing A will exist? Because if A belongs to little a belongs to closed set A, then A belongs to B complement and B complement is open. So by definition of open set, there is some basic open set XA comma A. such that x a comma a that is contained in B complement. Okay, the definition of open set. And this basic open set is contained in B complement. That implies uh, this basic open set has empty intersection with B. Okay, so for every A in A, we have a basic open set xa comma A such that intersection with B is empty set for every. So this is for some x A. So we define U equal to such union of such basic open sets xa comma A, where A belongs to A. Now similarly for little for each little b in the closed set B, we have some basic open set yb comma closed open yb comma closed D such that this intersection with this basic open set with A equal to empty set for some xb in x, and we define B equal to these basic open sets. Okay, so here why we have assumed that the smallest element A naught in so the smallest element is not a member of the closed sets A and B, because if suppose the smallest element A naught is a member of A, then if you consider A equal to A naught, then this does not make sense. So for such A naught, so for such A naught we don't have element xa. Okay, xa naught in X, such that this is neighborhood of the smallest element. Okay, so the case when the smallest element is a member of the closed sets A and B, that we deal separately. Okay, so what we have U equal to union of these basic open sets for every element A in A, and B equal to union of these basic open sets yb comma B for every little b in the closed set B. So in particular for each B in B, we have B belongs to this belongs to this basic open set. So B is open as a U and B. These are open sets because they are disjoint. So because they are union of basic open sets in the order topology. So open sets that is open. So U and B, they are open and they are open neighborhoods of A and B. So because A is subset of U and B is subset of B, so U and B, they are open neighborhoods of A and B. So it remains to prove that they are disjoint. U intersection with B, this is disjoint. So yeah, here we prove U intersection with B, this is disjoint. So now the proof is by contradiction. So if possible, we assume that Z belongs to the intersection. Okay, then Z belongs to U as well as Z belongs to B. So Z belongs to U means there exists some A such that Z belongs to X. So Z belongs to some basic open set XA comma a. So Z belongs to x a comma a, and Z also belongs to some basic open set y b comma b. So there exists so some little a in A and little b in the closed set B, such that Z belongs to uh, both both of the basic open sets. So x a comma a and y b comma b. So Z belongs to intersection of these two basic open sets. Now we consider two cases. So a so two cases. Case 1, a is strictly less than b and b is strictly less than a. So because a cannot be equal to b, because a belongs to a and b belongs to b, and a intersection with b equal to disjoint set, empty set. So a cannot be equal to b. So in the case 1, we consider a is strictly less than b. So if a is strictly less than b, then the intervals x a comma a and y b comma b, they must be disjoint, because if so it would be better if you draw a picture. So if a is strictly less greater than yb, then well, in this case we assume that a is strictly less than b. So now if a is lesser equal to yb, is lesser equal to is lesser equal to yb, so is lesser equal to yb, then they are disjoint, because this basic open set lies on the right hand side of this basic open set. So this cannot happen if some point z is in the intersection. Now if in the complementary case if a is strictly greater than yb, so a cannot be less or equal to yb. In this case these are disjoint. Now if a is strictly greater than yb, then one can see that a is strictly greater than yb and a is strictly less than b. So a belongs to this interval. Okay, so that is a lies between yb and b. So a is in the interval yb comma b. That contradicts that this has empty intersection with a. Okay, and similarly so interchanging the role of a and b, we can we would arrive at contradiction when b is less than a. Therefore we conclude that u and v, they are disjoint. Okay, so this proves the first case when the smallest element, the least element of x, that we denoted by a naught, so that is not a member of the closed sets a and b. So in the final step, we consider x as the least element a naught, and that is a member of one of the closed sets. Let's say that a naught is a member of a. Now we see this is closed open set. So this is open as well as closed. So this is closed open set. So if you consider immediate successor of a naught, so immediate successor of a naught prime, then A naught, close A naught, and open A naught prime. Open A naught prime, that is open, basic open set, and that is equal to singleton set A naught. And if you consider minus infinity, open minus infinity and close A naught, that is equal to a singleton set A naught, and this is closed. So this is closed open set. Now we consider the pair A, say difference with A naught and B. Okay, so this is closed. So this is closed subset of X, and this is by assumption B is a closed subset of X. So these are, so A and B close disjoint. So A minus X naught and B, they are disjoint, so, and closed, and the smallest element is not a member of A minus A naught and B. So by the previous case, we have disjoint open neighborhoods U and B of A minus A naught and B respectively. So now we consider U union with singleton set A and B. Then this is open, this is also open, and they are disjoint. Okay, they are disjoint neighborhoods of A and B respectively. Okay, so this completes the proof. Okay, so this is it. Thank you.